Hello, this is Roger Koch-Barr for the Bioelectricity course. We're in week 5, and this is lecture number 4. We're going to begin talking about some of the features of a 1D cable. It's called 1D because the spatial change all occurs along the x-axis. Let's just talk about the dimensions of our cable. So, if we think about this cable along one axis, we'll call that axis X. At different times, people sometimes call it X and they sometimes call it Z. For the moment, we'll call it X. We'll say that our fiber has only 3 important geometrical dimensions. It has a radius, which we'll call that A. It has the radius to an outer structure, that is to say the limit of where currents can be conducted. We'll call that B. And here we are assuming that B is very large indeed. There is a limit, but it's a big number. And then finally, we are on some occasions concerned with the length of the fiber. So if it goes from here to here, we'll call that distance L. But more often, we subdivide our cable into segments, and where it's subdivided into segments, we'll think of each segment. We subdivide into segments, we'll say each segment has a length delta X. Along axis X, there are currents. There's an intracellular current. I'll call that II. And when the intracellular current is positive, that means it's going in the same direction as X. There's an extracellular current, sometimes called an interstitial current. But here I'll use E so that it's easily distinguished from the number 0, E for extracellular. And when there is an extracellular current, it likewise flows in the direction of X. It's important to realize that that is a restriction because the extracellular volume is very large. So in general, currents outside the fiber can flow on all sorts of pathways. Right now, we are forcing our extracellular current to just flow in the X direction alone. Then there is membrane current. Membrane current flows across the boundary. You're familiar with that because we've talked about it so much in various other connections. When the membrane current is positive, we'll say that it's flowing from the inside to the outside. The 1D uniform cable model has resistance that's specified in various fashions. So we can say the bulk conductivity of the interior is rho I. The bulk conductivity of the extracellular is rho E. These are the conductivities in ohm centimeters, and we were talking way back there about seawater and how it is in the range of 25 ohm centimeters. That's what we're talking about here with rho I and rho E. Often the bulk resistivity, as it is called, is transformed into another form called Ri. And Ri is rho I divided by the cross-sectional area. So here that would be rho I divided by pi a squared. It's done that way because now Ri can be converted to the resistance, R, for the intracellular side, can be equal to Ri times delta X. That is to say, people create this entity Ri so that some of the calculation that otherwise would be necessary, rho I delta x over pi a squared, is already done in advance. A similar thing is done for rho e, using the radius b, but often then RE is rather small. This model of a fiber, where there is one dimension, we've called it X, currents along the fiber, intracellular, extracellular, membrane current crossing over. This is called the core conductor model. It's a simple model, but it was not made up by somebody in kindergarten. It is a model that was created, or at least perfected, by Lord Kelvin in England. This is the Kelvin for whom the unit degrees Kelvin is named. Kelvin made use of the core conductor model because he was a member of the scientific establishment in England when, at huge cost, a cable was laid from one side of the Atlantic to the other, and the cable failed. It did not work. So, a scientific committee, a review committee, was put together. Kelvin was a member of the committee to figure out what had happened. And in the course of doing that work, the work on the transatlantic cable, the mathematical model that was frequently used came to be called the core conductor model, because in that connection, this cylinder was a physical cable that went from England to the United States. Of course, we have adapted that work into an entirely different context, but the basic idea is much the same. In our case, we're thinking perhaps of a nerve axon that is possibly cylindrical. It's within a salt solution that surrounds it. So although much smaller and not going nearly as far, it is fundamentally similar in the currents that it carries to the transatlantic cable that was studied by Kelvin, and thus we use the core conductor model here just as he did there. Thank you for watching. I'll see you at the next segment.